All right, so problem number 7, let me read it out loud and then I'll explain what it means. It says, how large of an angle in radians and degrees does the diameter of the moon subtend to a person on Earth? Who in here knows what subtend means? Should, you probably talked about it in...
10?
No, subtend.
Oh, 10.
Oh, I thought it was subtend.
Yeah.
Subtend, no, it's subtend.
Yep.
It's the angle that you scan, so like, if the moon is here and I look at one side of the moon and then I scan to the other side of the moon, what is the angle between the two sides? So, in other words, for problem number 7, what we're doing is we're on the planet Earth, right? Here, let's make our Earth really pretty.
It's accurate too. It was. You're serious? No, it's right. I don't know what it is.
It's a pretty good actor. We're pretty close to it.
Oh, wow. Your Africa's a little far from your.
I'm trying to draw the entire planet in about 30 seconds so I can teach you guys physics. You're welcome.
You left off Tennessee. Jessica, you left off.
I forgot Tennessee. That's okay. So we're on Earth. This young man right here is standing up. He's in the UK. And he's like, hello, Governor. And
Now you're going to get the British people.
and now my British YouTube followers are going to be mad. And so we're talking about the diameter of the moon. So when you look up at night and you see the moon, what is the angle of the diameter? So what they're saying is when they say subtend, they're talking about what's this angle? Well, from here to here is the diameter of the moon. Okay? And I suppose you could think of this as like being like a y value and this being like an x value. So like think of it like this is the two-dimensional Cartesian plane. And the distance from here to here, so think of this as like x comma y.
Thank you.
And so one way that we could find the angle is that there's the relationship of the arc length is equal to the radius of the circle times the angle theta, which is usually in radians, right? In fact, well, it's not usually, it's always in radians. That's the only way that this relationship works. And so I don't know if you remember this or not, but they said for very small theta, so for very small theta, we can approximate theta at y over x. So in order to solve this, what do I need some information. Okay, I need some information. What information do I need? How far away the moon is from the Earth, and what else? I need an x and a y, so what else do I need? Diameter of the moon? Is that too obvious? Alright, so you might think, well, Mr. Adams, what is the diameter of the moon? Well, everybody knows that the diameter of the moon is approximately 3,500 kilometers. You guys knew that, right?
Yeah.
No.
So if the diameter of the moon, in other words, from here to here, this is about 35 or 3.5 times 10 to the third power. No, is it second power? 3,500 would be times 100. So this would be, yeah, that's right. Okay? Does that make sense? Now, if you didn't know that, guess what? In the back of your textbook, if you guys have your textbooks in front of you, on the very last page, it has physical data and solar system data. I think we may have, maybe at the beginning of the year, we might have talked about this. We're going to use this information a lot when we start to talk about orbitals. But it has the diameter of the moon, which is 3,500 kilometers. Then it also has the distance, the average distance from the moon to the Earth. So then we have this here, which is approximately 3.8 times 10 to the 5th kilometers. Okay? So that's pretty far away.
Hey, Gwen.
Hey.
How you been?
I'm recording.
Sorry.
Okay. We're glad to see you. Don't, just sit right there. Stop.
I'm gonna get the video shoot.
Yes, I don't want you in the video.
Why, Mr. Evans?
I think we all know why. No, because I don't want to edit the video. I mean, you're a very
Wait, what?
handsome young man, I guess. So now when I plug this in, 3.5 times 10 to the second over 3.8 times 10 to the 5th, and the kilometers cancel and all that stuff. This is in radians, so if I plug this in the calculator, I'm going to get a goofy answer. So I'm going to say 3.8, or no, I'm sorry, 3.5, and then I'm going to hit second e to the 2 divided by 3.8 second e to the 5th, and hit enter. Yeah, it's 9.2 e to the. Now, why do I get negative 3.5? Oh, because it's to the third, guys. I was right the first time. Why didn't you guys say anything? I was right the first time. So it's 3.5 e to the third divided by 3.8. Oops. 3.8 e to the 5th. Now I'll get the right answer. Yeah. So it's 9.2 e to the negative 3. Alright? So that's 9.2 times 10 to the negative 3rd radians. Okay? So this was 10 to the 3rd, not 10 to the 2nd. It's 3,500 kilometers, and it was 10 to the 3.5, 10 times 10 to the 3rd. I don't know what I was thinking. So anyways, it wants the answer in radians, but it also wants it in degrees. So you can do that cool conversion factor. But let's say you're taking a standardized test and you want to hurry up and get the answer right away. One thing that you could do is, this is in radians, right? If I make sure that my calculator is in degrees mode, and it is, I can go in and say second answer, right? Now, if I say 0.0092, and then this button that says apps, if I hit second and then apps, it pulls up the angle mode. And that's in radians, which is this little r, superscript r. So if I hit enter, what I'm saying is, I'm going to enter into my calculator 0.0092 radians. What mode is my calculator in? Degrees. So when I hit enter, it'll automatically calculate it in degrees for me. And you can do the same thing going from degrees to radians. And there's a conversion program on the calculator too. I just find this easier to do. So it's about 0.53 degrees. So this is the same as 0.53 degrees. So less than, well, it's a little bit more than a half a degree. So it's not even a whole degree. All right. Were there any questions? Does that make sense? Do you guys understand where the answers came from? Is that a small angle for theta?
Yeah.
Yeah. So that allows us to use that approximation value. And where that comes from is that when you compare the opposite length over the adjacent length is so much larger than the opposite. In other words, the diameter of the moon is orders of magnitude smaller than the distance of the moon from the Earth. And we use this a lot, like, you know, when they say like Jupiter is so many, we kind of use the reverse of this to calculate like how far away Jupiter is from the Earth. There's other things we do too, but mathematically we can do this too.